Hello everyone, welcome to Analog Communication Tutorials. In this video, I'm going to discuss on wideband frequency modulation. In one of my previous videos, I have discussed about single tone frequency modulation. That video will be a prerequisite for this video, so I highly recommend you to watch that before you continue with this. You can watch that video by clicking on the link shown in the top right corner right now, or I will leave the link of the same in the video description below. Coming to the topic of this discussion, which is wideband frequency modulation, let us start by considering the time domain expression for a frequency modulated wave, which is given by S of t equals AC cos 2 pi fct plus beta sin 2 pi fmt, where AC represents the carrier signal amplitude, Fc represents the carrier frequency, beta is the modulation index, and Fm represents the modulating signal frequency. Please note, I have derived this expression for frequency modulated wave in my previous video, which was on single tone frequency modulation. Now, looking at the equation 1 carefully, we find that this is of the form S of t equals real part of S tilde of t multiplied by exponential j 2 pi fct, where S tilde is the complex envelope of the frequency modulated signal and is given by S tilde of t equals AC into exponential of j beta sin 2 pi fmt. It should be noted, equation 3 represents the complex envelope of the frequency modulated signal S of t. Now, from equation 3, we understand that unlike the original frequency modulated signal S of t, which is given in equation 1, the complex envelope, which is given in equation 3, is a periodic function of time with a fundamental frequency equal to Fm. I repeat, S tilde of t, which is the complex envelope of S of t, is a periodic function of time with a fundamental frequency equal to Fm. Therefore, we can expand the complex envelope of S of t, which is S tilde of t, in the form of a complex Fourier series, which is given in equation 4 here. The expansion itself is given by S tilde of t equals summation n varying from minus infinity to plus infinity Cn into exponential of plus j2 pi n fmt, where the complex Fourier coefficient Cn is given by the formula Cn equals Fm integral minus 1 by 2 Fm to plus 1 by 2 Fm S tilde of t into exponential of minus j 2 pi n fmt dt. Now, if you look at the RHS of equation 5, you will find you have S tilde of t here. So, I will substitute for S tilde of t from the previous equation, which is equation 3, to expand Cn as Fm integral minus 1 by 2 Fm to plus 1 by 2 Fm, and this complete term is S tilde of t, and the following term, which is the exponential term, is directly taken from RHS of equation 5. Let me now take the constant AC towards the constant side here. So, Cn equals AC Fm integral minus 1 by 2 Fm to plus 1 by 2 Fm. Coming to these two terms in the RHS, you will see this is in the form of e to the power a multiplied by e to the power b, which can be written as e to the power a plus b. That is what is done in this part of the equation. So, exponential of a and exponential of b is given as exponential of a plus b. Now, I want to simplify this equation, which is equation 6. So, I am going to perform a variable change here. Let a new variable be considered called x and let it be equal to 2 pi fmt. As I said, I am going to perform a variable change. If you come to the previous equation, which is equation 6, you should note everything is denoted in terms of t. Now, I am changing that term t to a new variable x. Therefore, I will have to now find new limits of integration as well as the value for dt itself. That is shown in this part of the slide. To find the new integral limits, all you need to do is take the old integral limit and place it in terms of the old variable, which is t. So, coming to the integral, the lower limit is minus 1 by 2 fm. So, I will take when t equals minus 1 by 2 fm, x will be equal to 2 pi fm multiplied by minus 1 by 2 fm. 2 fm cancel in the numerator and denominator. So, what remains is minus pi. In a very similar fashion, when I take t equal to 1 by 2 fm, which is the upper limit of the integration, I will obtain x as 2 pi fm multiplied by 1 by 2 fm, which once again 2 fm get cancelled and what remains is pi. Lastly, to find the dt, I will differentiate equation 7 with respect to t, which is shown here. So, dx by dt equals 2 pi fm and differentiation of t with respect to t is 1. So, the answer is 2 pi fm itself. Now, since I am interested in dt, I will rearrange this equation to obtain dt as dx divided by 2 pi fm. Well, with that we have now found the new limits of integration as well as the value of dt itself. Let us now go back to equation 6 and replace these terms, which is shown here. Please note, this is equation 6 itself, which I have written for convenience. So, let us now substitute these values AC into Fm. Integral, the new lower limit is minus pi, the new upper limit is plus pi, followed by exponential of j beta into, please note, 2 pi Fmt itself is x, so it will become sin x, minus of, in the second term, if I take j and n outside, what remains is 2 pi Fmt, which is once again equal to x. So, the second term here will become j n x. Lastly, dt is replaced by dx by 2 pi fm. Now, coming to this equation, there is an fm here and there is an fm in the denominator here, they get cancelled. And I am going to take this 2 pi towards the constant side. So, it will be AC divided by 2 pi, integral minus pi to plus pi, exponential of, now you look at this, there is j common in both the terms. So, I will take it outside. It will be j into beta sin of x minus nx dx. This equation is very important because the RHS of this equation, except for a scaling factor which is equal to AC, is recognized as the nth order Bessel function of the first kind and argument beta. I repeat, the RHS of equation 8, except for the constant scaling term AC, is recognized as the nth order Bessel function of the first kind and argument beta. Now, the Bessel function so defined is denoted by the symbol Jn of beta and is given by Jn of beta equals 1 divided by 2 pi integral minus pi to pi exponential of j into beta sin x minus nx into dx. Now, if you compare equation 8 and equation 9, you will note that except for the scaling term AC, the RHS of both the equations are exactly the same. Therefore, I can write equation 8, which is Cn equals AC multiplied by Jn of beta, and that is shown in equation 10 here. So, the Fourier coefficient Cn is equal to AC, which is the carrier signal amplitude, multiplied by the nth order Bessel function of the first kind, which is Jn of beta. Having now found the value of the Fourier coefficient, let us now substitute this back into the equation for S tilde of t, which is defined in equation 4. Please note, I am talking about this equation, which is for complex envelope of the FM signal S of t. Therefore, we will get an answer as S tilde of t equals AC summation Jn of beta exponential of plus j 2 pi n fmt. This is for the complex envelope of the frequency modulated signal. Since I am discussing wideband frequency modulation and the idea is to obtain time as well as frequency domain representations of the frequency modulated signal. I'll now substitute for S tilde of t in the equation for the frequency modulated signal S of t, which is given in equation 2, which is shown here. Please note, I'm going to now substitute in place of S tilde of t. The substitution itself is shown here. So, S of t equals AC into real part of summation n varying from minus infinity to plus infinity. This complete term represents S tilde of t. However, the AC here is taken outside because it is a constant, followed by exponential of j 2 pi fct. In the next step, I am once again going to combine these two exponential terms. So, the answer would be AC into real part of summation jn of beta into exponential of j 2 pi fc plus n fm into t. Let us now interchange the order of summation as well as evaluation, and thereby we identify S of t as AC summation jn of beta into real part of exponential of j2 pi fc plus nfm into t. You should note that real part of the exponential of theta is equal to cos theta. Therefore, this complete term, which is the real part of exponential term, reduces to cos 2 pi fc plus fm into t. And this equation, which is equation 13, is the desired form of the Fourier series representation of single tone frequency modulated signal for an arbitrary value of modulation index beta. In simple words, equation 13 here represents the time domain representation of frequency modulated signal. Let us now plot the spectra for the single tone frequency modulated signal we obtained in our previous expression. For that, I am going to recall the equation, which is Fourier transform of AC into cos 2 pi fct equals AC by 2 delta of f minus fc plus delta of f plus fc. Now, if you come back to the equation for the time domain representation of the frequency modulated signal, you have cos 2 pi fc plus fmt in the RHS. Therefore, the Fourier transform of AC into cos 2 pi fc plus n fmt is given by AC by 2 delta of f minus fc plus nfm plus delta of f plus fc plus nfm. With this equation, now I can apply Fourier transform on both sides of the time domain representation for the frequency modulated signal to obtain S of f equals AC by 2 summation jn of beta delta of f minus fc plus nfm plus delta of f plus fc plus nfm. This equation, which is equation 14, is the desired form of the Fourier series representation of single tone frequency modulated signal S of t for an arbitrary value beta in frequency domain. I want you to note that equation 13, which is this one, represents the frequency modulated signal in time domain, and equation 14, which is given here, represents the frequency modulated signal in frequency domain. Having now identified the frequency domain representation for the frequency modulated signal, let us identify the frequency components in this equation and then move on to plot the spectra. The frequency components in this equation are Fc plus Nfm and minus of Fc plus Nfm. So, the frequency components are located at plus or minus Fc plus Nfm. It should be noted the n varies between minus infinity to plus infinity. So, there should be infinite number of frequency components once we start identifying the different values for n. Moving on, the amplitude spectra for the frequency modulated signal is shown in figure 1 here. Please note we have identified the frequency components as Fc plus n Fm. For n equal to 0, this frequency components result in plus or minus Fc. So, I will obtain an impulse at plus Fc as well as minus Fc. For n equals 1, I will obtain impulses at Fc plus Fm and minus Fc minus Fm. These impulses are shown here. You have Fc plus Fm and minus Fc minus Fm. Similarly, for n equals minus 1, you will have minus Fc minus Fm and minus Fc plus Fm. These impulses are shown here. So, we identify a pattern here, which is as the value of n increases, we obtain a frequency component on either side of the carrier signal frequency Fc. Also, since n varies between minus infinity to plus infinity, the number of impulses here are just infinite. However, we should note that the difference between these impulses come in the form of amplitude. Coming back to equation 14 here, which is the frequency domain representation of the frequency modulated signal, note that we have Jn of beta. The property of Jn of beta is such that as the value of n increases, Jn of beta decreases. This is a very important property to note. Before I move on to the spectra, I want you to note that the amplitude of this signal is AC divided by 2. Therefore, for n equal to 0, the amplitude of the impulse is AC divided by 2 multiplied by J0 of beta, which is shown in this particular part as well as at minus Fc. For n equals 1, the amplitude of the impulse is AC divided by 2 J1 of beta. However, you should note J1 of beta is less than J0 of beta. Therefore, the impulse that is drawn at Fc plus Fm as well as Fc minus Fm must be lesser than at plus or minus Fc. That is why we have shown shorter pulses. In a very similar fashion, we will find out that the impulses at Fc plus 2Fm and Fc minus 2Fm will be shorter than those at Fc plus Fm and Fc minus Fm. In this fashion, you can plot the spectra for the frequency modulated signal. Lastly, before we end this video, let us now list out a few observations that can be made by this amplitude spectra. We start the observations by noting down the fact that there is a carrier component present at both plus Fc and minus Fc, and the amplitude of this component is AC by 2 J0 of beta. And we have side frequencies that are symmetrically placed on either side of this carrier component at a distance of Fm, 2Fm, 3Fm, and it continues in this fashion. This can be verified from the spectra itself. If you start from Fc, you will note that to the right of this frequency component, you have Fc plus Fm, which is at a distance of 1 Fm. Then you have Fc plus 2 Fm, which is at a distance of 2 Fm, and it continues in this fashion. It should be noted we have such frequency components on either side of Fc, not just towards the right, we have towards the left as well. Let us recall that all those frequency components that appear to the left of Fc are called as lower sideband frequency, and all those who appear to the right of Fc are called upper sideband frequency. This applies to both positive as well as negative values of frequency. Coming to the second observation, which is really important, we say if the value of beta is much lesser than 1, then among so many Bessel coefficients which are given by Jn of beta, only two coefficients will remain, which are J0 of beta and J1 of beta. Therefore, for such a condition, when beta is much lesser than 1, the FM signal effectively comprises of only three frequency components, which is Fc and Fc plus Fm and Fc minus Fm. Now, I want you to recall the previous video, which is on narrow band frequency modulation. It is exactly this condition. That is, when beta is much lesser than 1, the spectrum as well as the modulation technique itself, what is discussed in this video, results in narrow band frequency modulation. However, if I consider the condition where beta is much greater than 1, then we will have a large number of Bessel coefficients which are Jn of beta. However, we note from the properties of the Bessel function that as long as the value n is approximately equal to beta, we will consider Jn of beta. The moment the value of n becomes greater than beta, the values of Jn of beta can be ignored. Moving on to the third observation, we note that the amplitude of the frequency modulated wave is equal to AC divided by 2, and this is also equal to the amplitude of the unmodulated carrier. That is, in simple words, the amplitude of frequency modulated wave is equal to the amplitude of the carrier signal. The next important observation comes in the form of power. Now, we should note the total available power for the frequency modulated signal is given by AC square divided by 2. Out of this total available power, the value of power that is carried by the carrier is dependent upon the value of J naught of beta, and the power that is carried by the sidebands depend upon the value of Jn of beta. So, we can say that if you want to compute the values of either the carrier or the sideband power in FM, we should know the values of the Bessel function coefficients. Well, with that, we come to the end of this discussion on wideband frequency modulation. In my next video, I'll talk about the transmission bandwidth of frequency modulated signals. So, stay tuned. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on analog communication. Thank you for watching. Have a good day.